Okay, so we had started talking about chapter 4 last time, and oh, hi Ben. Thanks. Oh, Caden is not here. I don't know where he is. He went home, apparently. Word on the street, anyways. All right, and chapter 4, we were talking about solving systems of equations. And we had kind of started talking about ways to do that. The first way that we had talked about was called graphing. So just to kind of review what that looked like. So we could have a system like this. To graph this, the first thing I want to do is to get these equations into slope-intercept form. So I'd want to get the y's by themselves. So the first equation, I can just subtract 4x from both sides. And the second equation, I'm going to subtract x from both sides, and then also divide by a -1. And then I'm just going to graph these two lines on the same axis. So remember, we were going to pick our points and try to pick them kind of far apart. Not like crazy far apart, but kind of far. So if I pick 0 for x, and I plug that in for x, I get 2 for y. And then maybe I'll pick 3 for x. When I plug that in, I get -10 for y. And for my other equation, let's see, we'll pick 0 for x, so that gives us -3 for y. And then maybe we'll pick 3 for x, and that gives us 0 for y. Oops! Ooh, that hurt. All right, so now I'm going to just plot these points and draw my lines. Let's see. 1, 2, 3. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So 0, 2, and then 3, -10. Draw my line. It's going to look like that, probably. And then I have 0, -3, and then 3, 0. Draw that line. It's going to look like that. So this guy is my solution. That looks like to me the point 1, -2, right? Now, are we positive that it's 1, -2 just from looking at the picture? No, right? That's going to be a little bit of an estimate. Is there a way that I could check to see if it's actually my estimate is correct? Sure. How would I do it? Go back to the beginning here and plug it in and see if it actually satisfies the equation. So 4 plus -2 is 2. 1 minus a -2, that is 3. So I am convinced this guy is my solution. Well, I would probably go back and look at to see if I made a mistake if graphing, or see if I just made a crummy estimate. Okay. So we had looked at graphing, right? We also looked at substitution. So let's consider that same system. And I'm just going to label these two equations A and B, just so I have a better way to communicate and talk about what equation we're interested in here. So the idea for substitution is I'm going to pick one equation and one variable from that equation and get that one variable by itself so that I can then use it to plug into the other equation. So if I look at this situation, there's really just one variable that would be a poor choice to try to isolate. What would be the one bad choice to try to isolate? It would be this 4x. Why is that going to be a problem? Because getting that x by itself, what am I going to end up having to do? Divide by 4, which is going to create fractions, which, again, aren't necessarily a problem, but if I can avoid having to deal with fractions, let's, like we have a lot of freedom here to choose what we want to do. I'm going to choose to not have to deal with any fractions, right? Makes sense to me. So let's just say, for the sake of argument, I choose to isolate this one. So to do that, I'm just going to subtract 4x from both sides. And I'm going to call that equation C. So what I do now is I'm going to substitute in what y is equal to for the y in equation B. And what I'm left with now is just one equation with one variable. So this I can now solve. So I'll go ahead and distribute the negative. I can combine the x and 4x together to get 5x. I can add 2 to both sides. And then divide both sides by 5 to get x equals 1. And now that I have that solution, how do I get the solution for y? I plug the x back in. Where should I plug it into? Equation A, B, or C? It doesn't matter. The best place to put it would be to C, because in C the y is already isolated, so it just saves me a little bit of algebra. But it doesn't really matter. Any of the A, B, or C would have been okay to use. And we see then our solution is 1, -2. Just like we saw when we graphed this, right? Okay? Everybody feel okay about substitution? What I want to talk about now today is a third method called elimination. So we'll do a couple of examples of elimination. We'll start with this same problem that we've solved 2 times already in different ways. So the way that elimination is going to work is I want to take a multiple of equation A and add it to a multiple of equation B so that one of the variables cancels out. Either the x's will cancel out or the y's will cancel out. So if I look at the 2 equations that I have right now, do I really need to, what multiple should, so if I look at the 2 equations right now, what do you notice about the variables? So if I added these 2 equations right now, as is, the y's would already cancel out. So the multiple of equation A that I need is just like 1 times equation A. And the multiple of equation B that I need is just 1 times equation B. So if I add these 2 equations together, 4x plus x is 5x. Y plus negative y is 0. And then 2 plus 3 is 5. I'm left with now 1 equation and 1 variable. If I divide both sides by 5, I get x equals 1. And then how do I get the value or the equation for y? Plug it back in. Does it matter where I plug it into? No. So maybe I'll just plug it back into equation A. And when I subtract 4 from both sides, I get negative 2. So I have the solution 1, negative 2. What do you notice about this elimination method compared to the previous 2 methods that we've tried? It seems like maybe this is the easiest and fastest of the methods we've seen. I kind of agree with that statement. And even better, elimination is one of these that scales really well. So as the problem gets more difficult, where we add in more variables and more equations, elimination continues to kind of be a better and better option. Because the nice thing about elimination, as you go through, the problem is getting smaller and smaller each time we do an elimination, which is nice. Not the case for substitution, where it kind of stays the same size. Let's do another example. So let's say we want to use elimination on this system. If I look right now, if I just add the 2 equations together, is anything going to cancel out? No. Okay. So in this situation, what I'm going to do is I'm just going to pick a variable that I'm going to make cancel out. So look at the coefficients on the x's and then the coefficients on the y's. Which one of them looks like the easier situation? The y's. Why did you say the y's? if I look at 2 and 6, those have a common factor, right? That's what I'd be looking for. If I compare that to 6 and 7, those are relatively prime. So the y's will be a little bit easier to use than the x's, but not significantly so. We'll do this problem both ways, but we'll start by trying to eliminate the y's first. Zach, you had a question? Very close. So if I multiply equation A by 3, that's going to make us positive 6y. Positive 6y plus positive 6y doesn't cancel out. Why don't we do negative 3 times equation A? I would recommend not doing subtraction. Let's do just multiplying through with a negative and keeping addition. My experience is students will almost always screw up a sign if they try to do subtraction. So if I do 3 times equation A, I'm going to get positive 21x minus 6y equals negative 54. And then equation B, we didn't have to do anything to. So I'm just going to copy that down. When I add these two equations together, I get 27x equals negative 54. And if I divide both sides by 27, I get negative 2 for x. How am I going to get y? I'm just going to plug that answer back into one of my starting equations. Let's just plug it into equation A. So if I subtract 14 and then divide by 2, I get the answer negative 2, 2. But we could have just as easily done elimination on the x's instead of the y's to start with. So let's try to figure out what we would need to multiply the equations by to make the x's cancel out. Notice that 7 and 6 are relatively prime. That means they have no common divisor between them other than 1. So what I'm looking for is I want to make the least common multiple of 6 and 7, which would be 42, right? 6 times 7. So what I'm going to do is I'm going to multiply equation A by 6 and equation B by 7. Equation A then is going to become 42x plus 12y equals 108. And then equation B is going to become 42x plus 42y equals 0. So when I add them together, the x's cancel out. They give me 0. 12y plus 42y is 54y. And that has to equal 108. And if I divide both sides by 54, I get 2. And then to find the x, I can plug that back into either equation. Let's just plug it into equation A. So 2 times 2 is 4. When I subtract 4 from both sides, I get 14. And when I divide both sides by -7, I get -2. So I have the point -2, 2. Was there really any more work doing it, eliminating the y's versus the x's? Not really, right? The only disadvantage was that maybe the numbers in here got a little bit bigger at one point, but not terrible. Lee? Of course. So you don't have to worry too much about the elimination, which variable you're choosing to eliminate. Just try to pick one that makes life as easy as possible. In this case, really, with 2 variables, it's really never going to be too bad, regardless of what you think. Do we have questions about what we've done so far? Okay. Well, we're going to stop here. This is as much as I